Hi everyone, welcome for this new session. My name is Arthur Strauss. I'm a recently graduated master's student in physics from EPFL, and I just started my PhD in quantum algorithms at CQT Singapore. Today I would like to present you the work I had the chance to realize within quantum machines, working on specifically high-level applications of quantum computing using the Quantum Orchestration Platform. And today I would like to showcase the concrete example of variational quantum algorithms and show you how the Quantum Orchestration Platform is actually a main enabler for enhancing performance of the execution of such algorithm. Diving right into it, so let's try perhaps to bring a bit more framework about how a variational quantum algorithm works overall. So the essence of those algorithms is that they are hybrid in essence. They combine the use of classical and quantum resources. And as you can see, it's working in a closed loop optimization schedule. So we have a classical computer that wants to evaluate an objective function. And this objective function will usually be the thing that the quantum computer will be in charge of evaluating. So as you can see, there is a set of parameter theta here, which is going to be fed. Those are real parameters that are going to be fed by the classical computer to the quantum computer itself. And the quantum computer, as you can see, runs this parameterized quantum circuit here and provides output that is then going to be interpreted by the classical computer to evaluate the objective function. And there will be a classical optimization subroutine fed in your classical computer in charge of re-updating the parameter set that you just set and feeding again the quantum computer with this new set of parameters and running this loop iteratively until you converge towards the minimum of your objective function. So this is the framework that we like to evaluate overall. And of course, this might seem very, very simple in the strategy, but there are actually multiple challenges that emerge from it. And the challenge that I would like to talk about, and where I think the Quantum Orchestration Platform is a major enabler and enhancer, is this quantum interface that you see here. So how do we actually perform this optimization of the scheduling of, first of all, retrieving the measurements from the quantum computer and then refeeding it back for a new experiment? So let's see how we can improve a bit the aspects of this setting. First of all, motivating a bit why this is a crucial factor. There are multiple challenges that are basically hard to benchmark for those classical quantum algorithms. First of all, we know that they suffer from a major caveat, which is the existence of potential barren plateaus, which can basically prevent us from converging towards an actual satisfying solution to our problem. So with this, we would have to find different strategies as perhaps to overcome those barren plateaus. Then there is the need of course, increasing drastically the number of shots in classical optimization steps in order to make sure that we converge towards the right solution and we don't suffer too much from the noise inherent from the statistical evaluation of expectation values. So those can, of course, play a significant role. And finally, the complexity of the cost function itself, like the objective function that we're trying to optimize, can be problem dependent and also can involve many, many runs on the quantum computer because usually can be a set of polystrings which are very impractical to cope with in reasonable times. So this accumulation of all those factors can basically lead to considerable runtimes. And this is where the QOP is here to basically reduce those runtimes and try to parallelize all the tasks as much as possible. So the Quantum Orchestration Platform is this overall framework that you see here, which basically carries at the core a pulse processor, which is in charge of running algorithms, real-time processing, classical processing, and the pulse generation and acquisition. And this is basically the processor that will interact directly with the quantum processor unit. And of course, this is framed directly with an old architecture designed for useful execution of your overall program. And the user can just compile the program using what we call QA, which is the pulse level quantum programming language that is attached to the QOP usage. And my goal is to show you that basically this embedding and this overall architecture enables significant changes in the way we realize VQAs. So first, let's start with the cost function evaluation. So usually on this part for VQAs, the cost function is usually a linear function, which is kind of helping because this means that the classical processing, which is required based on the measurement results, is actually not that heavy. For us, this means that it is easily computable in the pulse processor itself, in the sense that you basically are able to perform this computation on the fly as long as you're running the experiment and you do not need to sample all of your qubits, do the measurements, and basically retrieve them through the client PC. Everything can still happen within the controller in parallel to your circuit execution. And this is the second thing, right? Being able to run your quantum circuit at the same time as you're processing the information of previous ones is essential for reducing the overall latency that would acquire with each repetition of the circuit and with each optimization step that you're reaching out. Here is the example of a quack code that is in charge of basically evaluating the cost function of a max cut problem for a simple QAOA instance. And as you can see, there are a few lines of code which are very easy to write. And the idea is that this is everything that you need to cope with the function evaluation. Those few lines enable you to, first of all, process the results of your measurements. So this is done, again, by the controller itself. And based on the variable state that you see here, which contain the information about the measurement, whether the qubit was in 0 or 1, you can evaluate all of this while the next circuit is actually running with the same set of parameters. And the second thing is actually the way we give back the results to the user for running this optimization step, right? Like we want to refeed a new set of parameters for the next execution. And so this will usually be fed by this, what we call the input-output variable. And this is the only value that the user can sample if he wants. He doesn't have to retrieve all the results of the qubit measurements to basically perform this. He only has to sample one variable. And this setting of input-output is actually the way we also feed per set of parameters within the QOP. So to get an insight about how advantageous it is to use these input-output variables, let's try to see what is behind a usual traditional, I would say, VQA setting. So traditionally, what we encounter is that each time you want to run a quantum circuit with a specific set of parameters, you have to execute a new job. You have to launch a new instance because you're running a new quantum circuit. So to each quantum circuit is, of course, attached a new compilation, right? Because naively speaking, it is a new program that you're running. So there is a compilation, all the steps that you would imagine, breaking it down to some other unitaries and into your maybe set of gates. And so, of course, this can add a latency for each new quantum circuit that you're trying to compile. But of course, this is a bit the naive way to see it, because we know that in VQAs, we are usually working with ansatz. So the circuit structure is kind of always the same, right? It can even work by layers, for example. You could just choose among a set of unitaries what you would like to do. And so this is basically what the IO variables of the QOP enable you to take advantage from. In this setting, only one compilation is necessary. You only need to compile once the building blocks, all the pulses that you would need to realize your quantum circuits, and the parameters themselves are just being loaded individually. You do not need to load any other information because the gates that you have fed in are basically parameterized gates, which are directly informed by the parameters that are fed in real time by your processor. And as I said before, the cost function result is retrieved this time as a single variable from the processor instead of having to cope with multiple back and forth communication with the classical computer. And of course, on top of all this, the program is always the same. So you have one compilation and you can, in the same program, leverage all the real-time features that would enhance circuit fidelity, such as, for example, active reset for your qubits, while you are waiting for the parameter set to be fed for running your next iteration. In this graph is basically shown the comparison between the two settings I just described before in terms of execution time. So in the y-axis, we see the execution times in seconds, comparing the two methods I just described, and the number of parameters figures on the x-axis. As you can see, there is a 25 times improvement in the runtime execution for just the loading part of the parameters. So this graph only shows how quick we can gain performance by just loading the parameters in this setting and avoiding recompiling the circuit at every step. So, okay, summarizing very briefly, so we saw that VQAs in Core benefits from real-time added features. We can do real-time state estimation and qubit active resets, which leads subsequently to on-the-fly cost function calculation. And we can considerably reduce communications between the classical resources and the OPX, which is the main controller with our quantum processor. The question is now, can we do more? So actually the answer is yes. So there's been this proposal done by a team of Google earlier last year, basically trying to mix up levels of abstraction at the pulse level and at the circuit level. And the idea here is to leverage tools of quantum optimal control in the realization and the design of ansatz specific to VQAs. And so this strategy could perhaps open new states of research. And also what is very insightful is that we have right now through this kind of perspective, and navigation through different abstraction layers. And so we can directly see that a post-level programming language like Qua and the QOP overall can be a huge enabler for navigating in such abstractions, right? Because we see that encapsulation is a core concept in the QOP, and this unified vision of quantum control is actually at the core of it. So very briefly, all of these perspectives could lead to optimization landscape investigation. We could convert easily between expressibility and controllability. We can have deterministic time control and investigate all kinds of optimal control techniques for designing all sorts of unitaries that goes beyond the traditional gate model. So I hope it convinced you that the QOP offers a vision of unified quantum control that enables parallel execution of quantum circuits, and architecture is specifically designed for optimizing communications between classical and quantum resources. And finally, we see that there might be even more to come with this hybrid research that might be going on. So you can, of course, find us in other talks. I invite you to follow the talk of Yoav, which will follow tomorrow. And come say hi, of course, to our booth on our setting. With this, I would thank you very much for your attention and see you soon.